That's going to be equal to 2p plus 1, where p is 0. Okay, so let me give you guys a minute to copy all the algebra stuff down and make sure that's all okay. All right. I do want to explain why it's okay in this instance to reuse variables, because I bet you some of you guys are like, well, before you said let's not reuse variables, and all of a sudden now it's okay to do that. Okay. But are the algebraic steps okay, guys? I mean, nothing in there is past Algebra 1, hopefully not too difficult. All right. Let me ask you guys this question. Why is it okay for me to reuse variables going from case to case? So, go ahead, Ryan.
Because they're not related.
Because they're not related to each case, right? One case is odd, one case is even, okay? It's almost like if you guys are programming a subroutine, right? You have global variables and you have local variables, okay? So these are basically your local variables when you're defining case 1 and case 2. The global variable in this case is this guy right here, okay? So just trying to relate it as much as I can to computer science, since it is required for computer science majors. I just want to make sure like you guys see that there are connections between them. Okay, so everybody good with this stuff up to this point? Just one more thing to do. Okay, last thing we're going to do is say by case 1 and case 2, so this would be like our step 3. So by case 1 and 2, we see that x squared minus x plus 3 is equal to 2p plus 1. Okay. Both of those were equal to 2p plus 1, which is why I like to reuse the variables so that we don't have to say equal 2p plus 1 or equal 2m plus 1. Just makes it easier for us.
Would it always end up like that, where the two have the same?
If it's true. Yep.
Okay.
If it's not true, then you just use like the counter example over here, you might find that. But yeah, you can always manipulate it so that you get it to be the same form. Okay? And that takes a little bit of foresight, and that's why I'm trying to show you guys to reuse those variables to make it easy. Okay? So we could say by definition of odd, the original is valid. So that's why, and Mr. Rover, when you suggested like we don't have to write that like after each case, I was just being lazy so that way we can hold it off to the end, so that way we can save ourselves a little bit of writer's
Well,
cramp.
I knew you'd have to write it again.
That's correct, at some point, right. Okay. So guys, this is the division into cases, and what you guys are finding out is that it's not difficult, it's just a pain in the ass, okay? Because you're basically just doing the same stuff we already know again, okay? All right, questions I can answer before we try another one. Okay, so a secondary example. Okay. I want to prove that the sum of 4 consecutive integers is always even. Okay. Again, what you might wish to do is just pick 4 integers, add them up, and consecutive integers, excuse me, and make sure that it does work out. Because you don't want to go through and prove this and not have it work. Okay, so just off to the side really quick, I'm just going to write this, you guys don't have to copy it. Let's say 10, 11, 12, 13. Okay, those are 4 consecutive integers, nobody doubts that. Okay. 22, 33, 46. That's even, right guys? Okay. Let's just say I started with an odd number this time, right? Because so I could either start with an odd number, or I could just do 1 plus 2 plus 3 plus 4. That's going to be equal to 10, right guys? And that's even. So at least if and remember guys, that's the 2 possibilities. We can either start with an even number or start with an odd number, right? Guys, isn't it fairly obvious that if I start with an even or if I start with an odd, it's going to eventually end up being some sort of even sum for this, okay? So now it's our job to prove that for any variable, or I'm sorry, for any 4 consecutive integers, okay? All right, so everybody understands what we're trying to prove first of all. Okay, so let's go ahead and prove it. Okay, so we just need 1 integer for this case. Okay, so let's start by saying let's let x be an element of the integers. Okay, I'll put in brackets x arbitrary but particular. And that's all we know. Okay, we didn't say that x was even, odd, perfect square, anything like that. Okay. So it would lead us to believe that the easiest way to try to prove this might be even or odd. Okay, so let's try even or odd. Why not? Okay, so case 1. Let's let x be an element of z even. Because remember guys, the only two outcomes for this is if the first integer is even or if the first integer is odd, right? There's no other way that you can write 4 consecutive integers, okay? Regardless of what those integers are, okay? So, we already let x be an element of z even, okay? By definition of even, we can say that x is equal to 2k, where k is an integer. That's easy, right? We've done that literally dozens of times. Now we have to do a substitution step, right guys? So, if in terms of x, okay, so now we're going to do by substitution. Okay. How do we write the sum of 4 consecutive integers in terms of x, not in terms of k, right?
X plus x plus 1 plus x plus 2 plus x plus 3.
So, x plus 1 plus quantity x plus 2 plus x plus 3, right guys? That's 4 consecutive integers, right guys? And it doesn't matter what the first one is, and that is the sum of 4 consecutive integers. So think of the first number being 10. 10, 10 plus 1, 10 plus 2, 10 plus 3. Okay, does that make sense to everybody as to how we define consecutive integers? Not too difficult. Okay. By substitution, doesn't this become 2k plus 2k plus 1 plus 2k plus 2 plus 2k plus 3, right guys? That's all it is by substitution. Okay. Hopefully that doesn't hurt anybody's feelings. Donnie, does that hurt your feelings? Oh, darn. Not that I care if your feelings were hurt. Alright. What seems like the next most obvious thing to do at this point, guys?
Addition.
Combine like terms. Isn't this thing just beating you upside the head? We got so many k's and so many constants in there, let's just combine them. Okay? So we have some like terms. By combining like terms, 2k, 2k, 2k is 8k. And then by combining constants, 1 plus 2 plus 3 is 6. What are we trying to show about this thing?
It's even.
It's even, right? So what can we do with 8k plus 6?
Take a factor.
Factor it 2, and we're done, right? I mean, this one's really easy. 2, 4k plus 3, just by factoring a GCF, which is going to be equal to 2p, right guys? Or whatever letter you want to use. I'm just going to use p consistently, so that way when you guys are doing your homework, makes it really easy for you guys, so that way you don't try to figure out or utilize some other letter. Okay, so this is our GCF, and then this guy's by our integer closure. Okay, and of course we want to make sure that who's ever looking at this knows that P is not a vector space of magnitude 5 by 7. Alright, it's just an integer. Okay. So there we go, right guys? Nice and easy. This one's actually a little bit easier than the previous one, okay? As long as we know our definition of consecutive integers. Okay? So what's the bad news, guys? Yeah, we gotta do case 2, right guys? Alright, but that's okay. Usually, once you get case 1, case 2 is the same thing. You just plug in some different stuff. Okay, so let's go ahead and do case 2. Okay. So case 2. Let's let x be an element of z odd. By definition of odd, x is going to be equal to 2k plus 1, where k is an integer. So that's easy, we know that. And guys, isn't it the exact same steps? We just set up the consecutive integers, we substitute, we collect like terms, hopefully we can factor out a 2. Okay, so basically guys, it's going to be very easy to do the rest of it. Okay, so by substitution, x plus 1 plus x plus 2 plus x plus 3, quantity, sorry, is going to be equal to 2k plus 1 plus quantity 2k plus 2. If you want to write 2k plus 1, that's fine too. You could just go ahead and just squish it together. Just make it really easy on yourself. Okay. Plus quantity 2k plus 3 plus quantity 2k plus 4. So, everybody good with that, guys? Any questions? Okay, just substitution. There's a little bit of computation in there, but don't even sweat that. Okay. Just like the previous step, doesn't it seem obvious that what we should probably do is collect like terms, make this beast into something that's manageable? Okay, so we're going to combine some like terms. So by combining like terms, I think we get 8k plus 10 this time, as opposed to 8k plus 6. All right. And then clearly we can factor out a 2 and use closure, and we'd be done. Okay. So that's equal to 2 quantity 4k plus 5, which is equal to 2p, where p is an integer. Okay. GCF closure. All right, so let me leave this up here for a minute, let you guys copy all that down, and give you an opportunity to ask some questions if you have some. Okay. Anything I can answer for you guys, or algebra stuff okay? Not too difficult algebra stuff, a little bit sneaky sometimes, but this one's pretty straightforward. Okay guys, the good news is that now we're done with this. We just need the wrap-up statement. So we can just say by case 1, case 2, we could say that x plus 1 plus x plus 2 plus x plus 3 is equal to 2p. So, let me write that out. So, thus, by case 1 and case 2, x plus 1 plus x plus 2 plus x plus 3 is equal to 2p. Okay. And we proved that in the previous two. Okay, I mean, it's so obvious that we've already proved it, it hurts. Okay. So by definition of even, the original statement is true. So by definition of even, the original statement is true. All right. So the good news is that on the exam, I'm only going to give you guys like 10 or 15 division into cases proofs. I'm kidding. That's probably one. All right. Did I scare anybody for a second?
That was like really good.
Oh, it still takes forever to write it out.
Yeah, but.
Yeah, it's simple, I know what you mean. No, there's no time, yeah. So, okay. All right, what do we think, guys? Any questions I can answer so far about the division into cases? It's not difficult, okay? And again, it's really cool because this is a tie to some of the things you guys might remember from calculus, or maybe not remember, regardless. But at least I can show you guys like somewhere you guys have learned something and you can use it. Okay. Now, remember beginning class, we did division into cases and we used the quotient remainder theorem. And I said, okay, we're eventually going to get to a topic to where we can actually implement this division into cases and the quotient remainder theorem. Okay? So, let's go ahead and prove an example utilizing the quotient remainder theorem. Okay? So, what I want to do is I want to prove that the square of an integer has the form 3k or 3k plus 1. Okay? And I want to use the quotient remainder theorem using d equals 3. Okay? Now, let's think about like why this might be important to a computer program. Okay? If you're a computer, okay, just pretend for a second you're a computer, all right? You don't know the definition of even. You don't know the you don't know the definition of a perfect square, right? You have to have some way to tell if a number is a perfect square, okay? So, if a number doesn't fit this form, it's automatically not a perfect square, okay? Like for instance, okay, I'm trying to think of a number that's not a perfect square that probably wouldn't fit that form, okay? Maybe something like 21, well no, 21 works, but 23, okay? Guys, if you were to use the quotient remainder theorem, okay, with d equals 3, okay, wouldn't that be equal to 3 times 7 plus 2, right?
Mhm.
What can a computer automatically say about the number 23? Not a perfect square, right? So, for some reason, if a computer can figure this out, okay, then it says right away it's not a perfect square. Now, there are some numbers that kind of go against the grain for that. Like for example, if I gave you guys 24, wouldn't that be 3 times 8? And a computer might confuse that with being a perfect square, because it says it either has the form 3k or 3k plus 1. So this isn't the only test that a computer might use to determine if a number is a perfect square, but it's along the same lines. Okay? Now, somebody go ahead and throw out a perfect square for me. Be nice.
25.
25? Okay.